Hello, thank you for watching this video. I am David Solpic from Sorbonne University in Paris, and I'm going to present a joint work made with Andreas Feldman from Charles University about approximation schemes for clustering low highway dimension graphs. I guess the first question when you see that title is, what is the highway dimension of a graph? And it's a quantity introduced in order to model transportation networks that have some structural properties, like they have highways to go faster, and the hope is to find a dimension for those graphs that allow to bypass the standard worst case analysis. So what's at stake for us in that context? We want to develop tools for those networks and try to highlight some structural properties they have in order to understand them better and hopefully later on design better heuristics for them. We look at clustering problems for transportation networks because it makes sense to cluster geographical data. And in a theoretical standpoint, we want to go deeper into the relationship that highway dimension has with doubling dimensions. So what is our contribution for those questions? The main technical contribution of our paper, and the bulk of it, is a new hierarchical decomposition of graphs that have a small highway dimension. This decomposition yields some polynomial time approximation schemes for standard clustering problems, meaning we have good approximation for k-means, k-median, facility location. And furthermore, we show the NP hardness of those problems, meaning approximation is necessary. So the roadmap of this presentation is going to be, first we'll see definitions of highway dimension, of decomposition, etc. Then we'll see the decomposition itself. Then we'll see very briefly how to apply it to clustering problems. And finally, we'll have a glimpse on some technical details of the decomposition itself. Okay, so we start with the definition of highway dimension. We say that a graph G has a highway dimension H if for every ball B of radius 8R. So here's B, and 8 is a constant somewhat arbitrary, but say 8. There exists a set S of H vertices that are going to act as highways. So every long shortest path will go through one of these vertices. So formally, every shortest path in B that stay in B and that has length more than R has to hit S. So if you have a shortest path that is longer than R, it has to go through a highway. And that's the takeaway. You have only few vertices, the highways, or the entry points to highways if you want to see them as real vertices, that hit all the long enough shortest path. We won't need anything technical about highway dimension in that talk, but I wanted to define it for completeness. A result, very informally, is that a graph with bounded highway dimension can be randomly decomposed such that the following equation is true. I'll let you read it. It's for any vertex V of the graph and radius R and level I of the decomposition. This equation is true where beta VR is the ball centered at B and of radius R. So we have this scaling probability, and furthermore we have an interface set, which is a set of vertices. For every part we have that set of vertices that acts similarly as a vertex separator. So I'll give way more details later on, but this is to hint what I'm going to define next. What is the decomposition of a graph? This black rectangle is, say, a graph, and we start by finding a partition of it, and then we do that recursively. Every part of the partition is partitioned itself, and we want that the diameter of each part is divided by 2 at every step. So at level I, the diameter is 2 to the I. So for instance, the green level is level maybe 4, its diameter is 2 to the 4. Then the red level has diameter 2 to the 5, and the black level diameter 2 to the 6. Okay. So vertices of the graph lie in some parts of the decomposition at every level, and we'll want to somehow, the algorithm will want to consider each part independently, but it cannot be exactly true. We'll need to have informations on the other parts, so we want to have some way of connecting vertices to each other. This is done through interface. So an interface is a set of vertices, these crossed vertices, for instance, such that they approximately lie on every shortest path that crosses the boundaries. So if you want to go from one vertex in a part to a vertex in another part, going through an interface vertex incurs a detour only epsilon times the diameter of the part. Okay, so it's a small detour. So you can consider that every path goes through an interface. And that, at least that's the goal. And last definition we need to understand our decomposition is what cut means. So we say that the ball B is dashed, the part P is the red part of the decomposition, and we say that B is cut inside PP because B is entirely contained in P and lies in different parts of the green level. So we say that ball B is cut inside P and at level red. Now let's restate our main result with those definitions. So the scaling probability is as follows. The probability that the decomposition cuts the ball center at V on of radius R at level I is smaller than R divided by 2 to the I for every V, R, and I. So small balls cannot be cut at too high level or with tiny probabilities. And the interface is for a part P with diameter R, there exists an interface I, which is, we say, concise, constant size, and precise, meaning that the detour incurred to go through the interface to connect vertices that are cut inside P is epsilon R, epsilon times the diameter I. That's our main decomposition, that's our main result. So that's our main result, and we use it to clustering problems. For that, we use the framework defined in an article published at Fox 19, written by Vincent Cohen-Haddad, Andreas Spellman, and myself, which show how to use exactly that decomposition to design p-tasks, but in the case of doubling matrix. So we just find the same decomposition, and the framework directly plugs in. The key idea of that framework is that if a vertex is cut too high, meaning that some fixed ball around the vertex is cut at a level where the error epsilon times diameter is too big, then we deal with that vertex by hand. And the hope is that being cut too high happens with tiny probability because of the first property, because of the scaling probability. And so we can deal it by hand nicely. And all the other vertices, we can use the interface because epsilon R is not too big for them. That's the very general picture. If you want to discover more about it, I invite you to watch either the Fox talk I gave on YouTube or a talk Vincent gave at ESA, which is longer, about that Fox article. Now, as an intermediate conclusion, before digging into some slightly more technicalities, I invite you to come at the first portal session of ESA on Monday, September 7 at 1 p.m. and I'll be room 8 to chat with you if you want to. So now I'll try to give a quick glimpse on our decomposition. The first block, the building block of it, is a standard tool of high dimension graphs, which is the town decomposition. It's itself a recursive division of the graph that has the following properties. So first, for every part, there exists an interface set that has 1 plus epsilon multiplicative error. Going through this interface yields a 1 plus epsilon multiplicative error. So it's better than what we actually want. It's more precise than the interface we are targeting, but it has not constant size. It only has bounded doubling dimension. Okay. But there's an additional property, which is parts are somewhat isolated. So every subpart of the black one has some diameter, so associated with some level, whatever. But it's crucial because the rose part, for instance, at level I-2 has diameter 2 to the I-2. And there's a kind of moat around them of size 2 to the I-2 where no one lies. So the rose part has diameter r, and there is no one at distance smaller than r of that part. And it's true as well for the green parts. There's no one at distance 2 to the I-1 of the green parts, and for every other part. So we're going to use that property. So that decomposition is great, but there's two issues. There's no randomness. It's completely deterministic, so if someone is cut, then you cannot do anything. And the interface set is not concise. So I won't dig into the conciseness. I'll just explain how to get the randomness, the scaling probability we're targeting. The solution is briefly to randomly group the parts. Instead of decomposing one part into many parts with different diameters, we're going to group them kind of randomly. Okay, more precisely, we're going to define big and small later, but assuming we know what a big part is, we put the big part alone in their decomposition, in their parts, and then we group greedily the small parts. So we pick a small part randomly, and we put in the same part all the other small parts that are close enough. So we start that way, then for instance that way, and we keep going on like that. And as I said, big and small are defined randomly. Randomly such that the diameter of part at level I is between, say, half 2 to the I and 1.5 2 to the I. And among this range, the diameter is picked randomly. That ensures the probability property we want. Indeed, a tiny ball has a tiny probability of being cut, because if the tiny ball lies in a big part, then it cannot be cut, because the tiny ball, if it's tiny enough, it cannot be inside that part and another one because of the isolation property. We know that there is a moat around the big parts, so that ball must be completely contained inside the big part. So it cannot be cut there. can be cut only among small parts. And in that case, the greedy grouping ensures that the ball is cut with only a tiny probability, because the randomness could have been chosen such that the radius is slightly bigger and the ball could have been included into the part entirely. So, thank you for watching this video. Hope you get a few technical hints of what we're doing. If you want to know more or to understand better, I invite you to discuss with me at the first poster session. Here are the details again. Or if you want to discover more about how to use this decomposition, you can see either my presentation at Fox or Vincent Cohen at his talk at ICERN. Thank you again and see you Monday.